Okay, these are some points related to Longley rice that we have seen. Then Okumura model, it comes in 1968. Okay, and read the fourth point. One of the most widely used model for signal prediction in the urban areas. Okay, so it is applicable for the urban areas. Then some parameters are given for the Okumura model. It is applicable for the frequency range from 150 megahertz to 1920 megahertz. It can be extended up to 3 gigahertz. So it can be applicable for ISM band up to 2.4 gigahertz. And it covers the distance from 1 kilometer to 100 kilometer. Okay. Now, this is a very, very important equation. You can quickly write the equation of loss calculation. It is L50 dB is equal to LF plus AMU. It is a function of frequency and distance minus GHTE minus GHRE minus G area. So the term which are included in loss calculation, the L50 dB means it is the 50th percentile. That's why it is called as a 50. Okay, it is called as a median. It is called as a median value of path loss. This is the equation of path loss by considering the median. Then the first term is LF. What is LF? It is the free space propagation loss. So in last lecture, we have seen the equation for this free space propagation loss. Can anyone tell me what is the equation for that? Free space propagation loss? Can anyone? Actually, this equation is minus 10 log of lambda square divided by 4 pi square d square. So here I mention also LF. LF is the free space propagation loss. Its equation is minus 10 lambda square upon 4 pi square d square. Okay, plus AMU, it is attenuation. It is attenuation related to free space. How it can be calculated, that we will see next slide. Minus GHTE. T is nothing but the transmission. Okay, it is the gain of transmitting antenna minus gain of receiving antenna minus gain of environment. Minus gain of environment. You make the box for this equation. It is very, very important equation. The path loss in Okumura model, L50 is equal to LF plus AMU FD minus GHTE minus GHRE minus G area. Okay. So there is no any shortcut how we can recognize or how we can memorize this equation. You have to read it carefully and memorized it very carefully because based on that the numerical of 6 to 8 marks may asked. Okay, finished this equation? Yes or no? Complete or not?
Yes, sir, completed.
Okay, you actually respond me. Okay, then this is a graphical method. It is called as an empirical method. Okay, so in that, how to find out the attenuation? So this term AMU F comma D. So F is the frequency and D is the distance between transmitter antenna and receiver antenna. Okay. Now here, if you see the right side, x-axis indicate the frequency. X-axis indicate the frequency. It is in megahertz. Now there are two y-axis. The first y-axis is nothing but the distance, d. See the cursor. D is the distance between transmitter antenna and receiver antenna. And second most y-axis is nothing but the attenuation. Here in it is mentioned that A is a function of F comma D, and it is mentioned in decibel. It is mentioned in decibel. Now we know this Okumura model is applicable for the urban area. Okay. Now here uh, they mention the HR, height of the receiver antenna is 3 meter, and height of the transmitter antenna HT is equal to 200 meter. So this is one of the example actually. Now, from this, how we can calculate the attenuation AFD? Okay, so here I will give one or two examples. Hmm? Now, here in your problem, the frequency is mentioned and the distance between the transmitter antenna and receiver antenna is mentioned. Okay, for example, the distance between transmitter and receiver antenna is 10 km. Okay, so here you see the first y-axis, which is of distance d in kilometer. So here 10 km means this graph. So here you can consider this graph 10 km like this. Okay. Now it operates at a frequency of 500 megahertz. It operates at a frequency of 500 megahertz. Then you consider this is a 500 megahertz. So this 500 megahertz, you can draw a straight line, like this, and on 10 km where it get intersect, on 10 km where it get intersect, for example at this point it get, sorry, at this point it get intersect. Now from this point you draw one horizontal line, which intersect the second y-axis, so where it get intersect, you consider that value. I think it is in between 20 and 30. It is in between 20 and 30, and which is more closer to the 30. That's why approximately you can consider it as a 26 or 27. Okay, 26 or 27 dB. So in this way you have to calculate the value for attenuation, by using Okumura model. Got it? Yes or no? It's very simple actually. Yes or no?
Yes, sir.
Okay. Second case, it operates at a frequency of 1000 megahertz, and distance between the transmitter and receiver antenna is 70 kilometer. 70 kilometer. Then this one is 70 kilometer graph. This is 1000 megahertz frequency. You can draw a straight line for this 70 megahertz, sorry, 70 kilometer, and from that you draw a horizontal line. It get intersect in between 50 and 60. You can consider it as a 55 dB. In this way you have to calculate the attenuation. Okay, clear? Yes or no? Okay, so this part is over. How to calculate this one? Now here the gain of transmitting antenna and gain of receiving antenna, it has some equations given. So these equations are like this one. For transmitting antenna gain, GHTE is equal to 20 log of HTE. What is HT? HT is the transmitting antenna height divided by 200, and certain the height is in between 30 meter to 1000 meter. Then for receiving antenna gain, two equations are given. One is when the height is less than 3 meter, and second one is when height is in between 3 meter to 10 meter. The equations are here. You can write it quickly, or if possible, you can draw this graph also. Once you finish, tell me quickly. I will give 2 minutes only. Finished? At least say something. Wait, sir, or finished.
Yes, sir.
Done, sir.
Okay. You wrote the equations also, because these equations are required at the time of calculation. Okay. Now, uh, if you drawn the graph, indicate two cases on that. Uh, the antenna operates at a frequency of 500 megahertz, and the distance between transmitter and receiver antenna is 10 kilometer. What is the attenuation? What is the attenuation occur? What is the attenuation value? So here you can intersect it and find out the attenuation. You can mention on graph, this is the attenuation. And in second case, consider 1500 megahertz frequency, and it operate and the distance between transmitter and receiving antenna is 60 kilometer. Okay. Now, the question in your mind may be, if the distance is 41 kilometer, distance is 42 kilometer, distance is 43 kilometer, then also consider 41, then likewise you have to draw the graph this way, likewise. Okay, finished? Can we move? Clear this concept? How the Okumura model helped to find out the loss, path loss?
Sir,
Uh-huh.
sir, I have a question.
Yes.
Sir, in this first and second formula, sir,
Mhm.
in the first formula, the value is taken 20 log h of t divided by 200, and in second, it is taken as 10 log. Sir,
Hmm.
why it is different? 20 means
Actually, here there is certain condition. Okay, when we take 10 and when we take 20, actually, I think it is covered in uh, signal and system. Your subject is there, and one more subject is there. Okay, when we consider 10 and when we consider 20. Can anyone? It's a mathematical.
Sir, if voltage is there, then we consider 20 only.
When voltage is
When voltage is there, then we consider 20 only, and in another cases 10.
50% correct, because in this case the signal is signal. There is no any question of voltage and current and like that.
sir, in this case, there is no relation of voltage, na, sir?
Yeah, there is no any question of voltage. Actually, it is asked in oral at the time of oral. Why you consider 20? Why not 10? There is a logic. Can anyone? Okay. At the end of lecture, I will tell you. तोपर्यंत कोणाला जर आन्सर मिळत असेल तर पहा. ठीक आहे. This one is finished. Now, Okumura again uh, give the empirical model for open area, then quasi-open area, and suburban area. Okay, in order to calculate the correction factor, that is called as a G area, the environmental gain. This point. Generally, we consider this environmental gain is equal to zero. Is equal to zero. But for that also, Okumura give the empirical model. Here the frequency is given, and likewise you can draw the uh, straight line. For example, for 7 megahertz, you plot the straight line and intersect it and find out the that G area value. Okay. But in most of the cases, this G area gain of the environment, we consider it equal to zero. Okay. Now, there are certain drawbacks and disadvantages of Okumura model. That the most important thing is that the Okumura model is mostly depends on graphical data. If a mu of f of d value is not there, then we cannot find the path loss, isn't it? Isn't it? If this value is not there, not given, then we cannot calculate the path loss. And this value is calculated by using this graph only. If this graph is not there, then we cannot calculate the value. That's why this is the drawback of Okumura model. that it mostly depend upon the graphical data. Again, next one is that this model is invented in Japan. Okay, so it is not necessary that it work effectively in India. That's why the Okumura model is not so much accurate, you can say. The Okumura model is not so much accurate. Okay, certain points for related to Okumura models are mentioned here. Okumura model is wholly based on measure data, means the empirical or graphical data. There is no analytical explanation. काय analytical explanation नाहीच आहे तिथं, बरोबर. In certain cases, the curves can be extrapolated. तो ती जे curves आहेत, for example, here I want the AMU value for 45 kilometer. Then consider here 45 kilometer, and you have to extrapolate this curve and then calculate the value. That's why the data is extrapolated. Okay, this is one of the drawback. And Okumura model is one of the simplest and most accurate path loss predicted model at the time of 1968. At the time of 1968, but as it depends upon mostly the graphical values and it is extrapolated, that's why it it is what we can say, it is considered as inaccurate after 1968. Okay, that's why in 1990 the Hata modified this Okumura model only. The Hata is the name of scientist only. He modified the model of Okumura, and that model is called as a Hata model. In that it nullify, or it reduces, or it reduces the dependability of AMU by using the graphical method. So here the Hata model is totally depends upon a equation. So that equation is given. So loss L50 dB is equal to 69.55 plus 26.16 log of FC, and that FC is in megahertz only, minus 13.82 log of ST minus A HRE. This is again a new parameter, plus 44.9 minus 6.55 log of STE into log of D. D is the distance between transmitter and receiver. Now, unfortunately, there is no any way to find out the expression for this one. You have to consider this equation directly. You have to memorize this equation at any way. याला काय शॉर्टकट नाहीये, कसं ध्यानात ठेवायचं. बाय युजिंग और बाय प्रॅक्टिसिंग तुम्हाला ते ध्यानात ठेवावं लागणार आहे. ओके, सो हे पाठ करायचं इक्वेशन, अँड रिमेनिंग व्हॅल्यूज are taken from the problem. Some of the values you have to calculate, put all the values in that one and calculate the path loss. Okay, so here directly the equation is given in order to calculate the path loss. Okay, so here the dependability on graphical data is get reduces. That's why Hata model is more efficient as compared to, or more efficient or more accurate, you can say. It is more accurate as compared to the Okumura model. Okay, so you write the equation, then write the terms. HTE, this is the base station antenna height, this is the receiver antenna height, and AHRE is the correction factor. And what is that correction factor? Again, it is depends upon some parameters that we will see in next slide. Quickly you write it. Don't forget any term. Finished?
Yes, sir. Okay.
Okay. Then here the AHRE is the correction factor for effective mobile antenna height, which is the function of coverage area. So A is for the area actually. So here again the area, it depends upon the size. Medium size city, large size city, path loss in suburban area and open rural area. Okay, again you have to memorize all these equations, but mostly the equation for large size city you have to consider, mostly the problem asked on that. Okay, so the second box is very important, so you take the screenshot or you write quickly the equation for AHRE. Finished? Okay. So here this is about the Hata model. Then extended Hata model, it is also called as a cost 231 model. Keep in mind, extended Hata model, it is also called as a cost 231 model. So what is the difference between this Hata model and extended Hata model? So Hata model is applicable for 150 megahertz here, 150 megahertz to 1.5 megahertz, and extended Hata model is applicable for 150 megahertz to 2 megahertz. So in short, you can write the extended Hata model is applicable for 150 megahertz to 2 megahertz, while the Hata model is applicable for 150 megahertz to 1.5 megahertz. Then write the terms. Write the equation.